Hi everyone. In this video, we are going to be using the rational zeros theorem to solve a polynomial function. Okay, and like I said in previous videos, this is going to be a particularly tedious section. Okay, so this section takes time, but it is a pretty powerful tool that we have for solving polynomials if you have to do them by hand. All right. And also in this section, we're going to assume that all of these functions have at least one rational zero. All right, that's important. And let's go ahead and go over the rational zeros theorem again, just so we remember what it is. So the rational zeros theorem says if we have some nth degree polynomial h of x, okay, so it's of this form here. All right. If h of x if it has a rational zero, which again, we're not always guaranteed that, but if it has a rational zero, then it can be written as the form p over q, where p is a factor of a sub zero. So that'll be our last term here. All right. And q is a factor of a sub n, which is the leading coefficient in our polynomial. Okay. So let's see how we can use this to try and fully factor a polynomial. So here we have f of x is equal to 2x to the third plus 7x squared plus 2x minus 3. All right, so we know that all of our rational zeros are going to be of the form p over q, where p is going to be a factor. P is a factor of a sub 0, or in this case, negative 3. All right, and then q is going to be a factor. Q is going to be a factor of 2. All right, or a sub n. So let's go ahead and list these. So factors of negative 3 are plus or minus 1 and plus or minus 3. And then factors of 2 are going to be plus or minus 1 and plus or minus 2. So we got lucky with getting a couple of prime numbers here. That makes this not quite as bad. So all of our possible zeros are going to be, let's write this out, possible zeros. And again, you can check this by checking all possible combinations here. But we're going to get 1, we're going to get minus 1. We'll get 1/2, we'll get minus 1/2. We're going to get 3 over 2, we'll get minus 3 over 2. And then we'll get 3 and negative 3 as well. Okay, so these are all of our possible zeros here. All right, so there's not too many of them. But I will say the only way to know for sure is to go through and check each of these. And I would just recommend going straight left to right. But for the sake of making this video shorter so that you kind of get the idea, let's go ahead and make a lucky guess. All right, and say that our first choice is going to be negative 1. We're going to check to see if negative 1 is a 0 here. I'd already figured this out going in just to make this video shorter, but normally you'd have to go through and check a bunch of these to figure out which ones are going to be your actual zeros here. Okay, but we're going to make a lucky guess, like I said, and check negative 1 first. Okay, so let's do that now. So remember, to do this, we can use synthetic division. All right, so let's do that. So remember, we're going to put all of the coefficients of our initial polynomial. So we'll have 2, 7, we'll have 2 again, and we'll have negative 3. And we'll put negative 1 out here. And we'll go ahead and bring this 2 down. So 2 times negative 1 is negative 2. 7 plus negative 2 is 5. 5 times negative 1 is negative 5. 2 plus negative 5 is negative 3. Negative 3 times negative 1 is positive 3. Negative 3 plus positive 3 is 0. So look at that. We know that negative 1 is indeed a 0. So what that also tells us then is that x plus 1 is a factor of f of x, okay? Because if we plugged in negative 1 here, we would get 0 for x plus 1, okay? So x plus 1 is a factor of f of x, and that means now f of x can be written as x plus 1 times 2x squared plus 5x minus 3, okay? And remember, each of these coefficients come from our synthetic division here, all right? We don't have any remainder because this was indeed a 0. All right, so now all we have to do is see if we can find the zeros of this polynomial here. And to do that, we're going to just use the quadratic formula. Anytime you get something like this, there are other ways of factoring it, but I tend to find the one that works every time. Not fine, this is true. This will always work. You can use the quadratic formula. So we have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Or, and since we're just doing this polynomial here, these are the coefficients we're worried about here. So we'll have negative 5 plus or minus the square root of b squared, or in this case, 25 minus 4 times a, which is 2, times c, which is negative 3. And this is all going to be over 2 times a, or okay, so we'll have negative 5 plus or minus the square root of 25 minus 4 times 2 times negative 3. Okay, so it's be 25 minus a negative 24, so 25 plus 24, all right, which is going to give us 49. And this is all going to be over 4. Okay, so we'll have negative 5 plus or minus 7 over 4. Okay, so negative 5 plus 7 over 4, that's going to be 2 over 4, or 1/2. Okay, and then negative 5 minus 7 all over 4 is going to be negative 12 over 4, or just negative 3. So our other zeros are 1/2 and negative 3. Okay, we're going to go down here. So we'll scoot this down. Okay, so if 1/2 is a 0, that means we can write f of x is, or can be written as x plus 1. That was from our first synthetic division. X plus 1 times x minus 1/2, because 1/2 is a 0, times x plus 3, because negative 3 is a 0. Okay, and if you want to double check this and FOIL this out entirely, just to confirm that this is in fact a 0, that is fine. All right, so there we go. These are our zeros here, and we have fully factored this polynomial. All right, and if we want to, I guess actually let's just go ahead and fully FOIL this back out, just so we can confirm that we're actually correct about this. So if we want to, let's go ahead and do this first one here. So this will give us x squared minus 1/2 x, okay, plus x minus 1/2. Okay, we'll have that times x plus 3. All right, so we can combine like terms here, and we'll get x squared plus 1/2 x minus 1/2 times x plus 3. And we can FOIL this out. So we'll get x to the third wait, where's the mistake? We made a mistake here somewhere. Let's double check this. Okay. Let's see. Oh, I know where we made it. It's not really a mistake. It's just the way we were writing all of this. We can also write, sorry, this is relevant here. Okay. So if you're going to check your work, sometimes you have to be careful about this. X minus 1/2 can also be written as 2x minus 1. Okay, so if we think of it like x minus 1/2 is equal to 0, we can multiply both sides by 2. Okay, so if you're checking your work and you don't get exactly the polynomial back, but maybe you get some multiple of the polynomial back, this is why this might be the case. So let's go ahead. let's go ahead and keep going like we had, and I'll show you why this is relevant here in just a minute. Okay, so if you're ever checking your work, I'm going to show you why this is relevant here. So, okay, let's go ahead and fill this out. So we can have, so we'll have x to the third. Okay, so then we'll have plus 3x squared plus 1/2 x squared plus 3/2 x. Okay, and then we'll have minus 1/2 x minus 3/2. Okay, so let's see what this looks like. So if we combine all like terms, we'll have x to the third. Okay, we have x squared plus 1/2 x squared, so that would be 7/2 x squared plus x minus 3/2. So if we're right, this should be a multiple at the very least of our initial polynomial. Okay, so if we multiplied everything by 2 to make sure this coefficient is the same, if we multiply everything by 2, we will get 2x to the third plus 7x squared plus 2x minus 3. And that is the same thing as our initial polynomial. Okay, so that's important to note. So if you're ever checking your work here, okay, so we got it all right, that's fine. If we're ever checking your work here, it's important to know that this particular thing that I was talking about here, okay, is the same thing as 2x minus 1. Okay, so really multiples of polynomials are the same as those initial polynomials, at least in this context here. Once you've set it to 0, you can multiply both sides and it'll end up being the same. This is just following the basic rules of the equality sign. If we've set the polynomial equal to 0, you can multiply both sides of the polynomial by any number you want, and it will end up being the same. Okay, so really what we did here was we just multiplied this one by 2 in order to get this back. Okay, sorry, that's kind of a long-winded explanation here. You don't, given how tedious this is, you definitely don't always have to double check your work on these. But if you ever have a little bit extra time on a test, it can be helpful in certain situations to go back and double check your work. Okay, so there we go. That's also just to show you that sometimes even people who like to do math professionally sometimes get a little lost there for a second. It happens every now and then. It's okay. But you just got to work through it, and you will hopefully get to where you need to go. All right, so let's take a look at this next one. We have h of x is equal to 5x to the fourth plus 24x to the third minus 76x squared plus 9x plus 14. Okay, and we want to use the rational zeros theorem to find all possible zeros of this polynomial. Okay, so we know that all of our possible rational zeros are going to be of the form p over q. Okay, where p is a factor of a sub 0, or in this case 14. Okay, just to double check, back up at our theorem here. P is a factor of a sub 0, and q is a factor of a sub n. So then we're going to have factor of 5 here. Okay, so let's go ahead and list all of these. So factors of 14. So we're going to have plus or minus 1, plus or minus 2, plus or minus 7, and of course, plus or minus 14. Factors of 5, this is a prime number, so we're just going to have plus or minus 1 and plus or minus 5. All right, so now let's go ahead and list all of our possible combinations. So we're going to get 1, we're going to get negative 1, we're going to get 1/5, we're going to get negative 1/5, we're going to get 2, negative 2, we're going to get 2/5, negative 2/5, all right? we're going to get 7/5. We're going to get negative 7/5. We'll get 7, negative 7. Okay, we're going to get 14, negative 14, and then we'll get 14 over 5 and negative 14 over 5. Okay, so when you get to these bigger polynomials here, especially when you have lots of factors for each of your P and Q, right? You're going to have a lot to choose from, okay? And again, we're going to make a couple of lucky guesses here. But let's start with 2, okay? So we're going to start with 2, all right? So if we start with 2, it's again, lucky guess, so we're going to start with 2, all right? We can use synthetic division to go ahead and see if this is a factor. So we'll put our coefficients in. About 5, don't need the comma there, 5, 24, negative 76, 9, and 14. Okay, and again, you will have to go through in the homework and check which of these are which. Yeah, that would be my. Yeah, I don't have any good tips here to find out which ones are more likely or which ones are less likely. Sometimes it's just good to practice synthetic division, I guess, right? Okay, so let's go ahead and bring down the 5. So we'll have 2 times 5. That's 10. Okay, so 24 plus 10 is 34. 34 times 2 is 68. Okay, so if we have negative 76 plus 68, that'll give us minus 8. Okay, 2 times negative 8 is minus 16. So 9 plus a negative 16, or minus 16, is negative 7. Negative 7 times 2 is negative 14. 14 plus negative 14 is 0. So look at that. We have a remainder of 0, no remainder. So that means that x minus 2 is a factor of h of x. Okay? And this also means that h of x can be written as x minus 2 times 5x to the third plus 34x squared minus 8x minus 7. Okay, so if you have a degree, if you have anything higher than degree 2 polynomial left over, so we were given a degree 4 polynomial to start with, that means we're going to have some binomial times a polynomial of degree 3 here. If you're given a degree 3 or higher, I would just keep checking zeros here, okay? But one of the nice things about this, really you have a couple of options. You can keep checking zeros with your well, let me back up just a second here, okay? So one of the nice features of this is that if each of these possible rational zeros are also a possible rational zero of this particular polynomial as well, okay? However, if you want to narrow it down a little bit, what you can do is we can do this process all over again. So we can say P over Q, okay, where now we need to use the rational zeros theorem to narrow this one down, to find out which possible rational zeros are here, okay? So here we're going to have a factor of negative 7 over a factor of 5, okay? Factor of negative 7 over a factor of 5. All right, so let's list all of our factors of negative 7. Okay, so we're going to have plus or minus 1, and we're going to have plus or minus 7. And we're going to have plus or minus 1 and plus or minus 5. Okay. So that means that all of our possible zeros, are going to be 1, -1, 1/5, -1/5. We're going to have 7, -7, and we're going to have 7/5, and then -7/5. Another option you would have had is you could have taken all of these original rational zeros here, and you will know that these could also be rational zeros for this polynomial as well. But if you do the rational zeros theorem again, you actually narrow it down a little more. But we're going to make a lucky guess on this first one again, and we're going to choose -7. Okay, so we'll have -7, and now we're going to put the coefficients of this polynomial here in here for this one. So we'll have 5, we'll have 34, we'll have -8, we'll have -7. So now we go ahead and bring down the 5. Okay, so -7 times 5, that's going to be -35. So we get -1, -1 times -1 times -7 is +7. So -8 plus 7 is -1. -1 times -7 is +7. So -7 plus 7 is 0. And that means that we are going to have -7 is indeed a 0. So that means that x plus 7 is also a factor of h of x. And therefore, h of x can be written as, we said, x minus 2 times x plus 7 times, we'll have 5x squared minus x minus 1. Okay, so now we're getting much closer now. Okay, so now we have gotten it down to 2 binomials and another polynomial of degree 2, or a quadratic polynomial here. So now we can just use the trusty quadratic formula to go ahead and simplify this even further. So we'll have x is equal to negative b, or in this case, it'll be negative 1, so we'll have +1, plus or minus the square root of b squared. Well, we'll just be consistent here. Okay, plus or minus b squared, so we'll have -1 squared minus 4 times 5 times -1, all over 2 times 5. Okay, so let's go ahead and simplify this. So we'll get 1 plus or minus the square root of 1 minus 5 times 5, or 4 times 5 times -1. That'll be a -20 all over 10. So we get 1 plus or minus the square root of 21. So because 1 minus a -20, that's 1 plus 20. So we get 21. All right. This will all be over 10. Okay. Or we can get 1 over 10 plus the square root of 21 over 10. And then we also have 1 over 10 minus the square root of 21 over 10. So that means that h of x can be written as, we can write h of x as x minus 2 times x plus 7 times x minus 1 over 10 plus the square root of 21 over 10 times x minus 1 over 10 minus the square root of 21 over 10. Okay, and I'm going to skip this step, but you should be able to just go ahead and multiply all of these together, and you should get either a multiple of your original polynomial or your polynomial back. And if it's a multiple, that just means that at some point along here, you could have multiplied one of these by a constant and everything would have been fine. Okay, so let me just do a quick breakdown again about how these work. So here what we did was we started with this polynomial, okay? And what we did was we factored out a single binomial from that, which we said was x minus 2, okay? So then we rewrote it as x minus 2 times the polynomial that we got from our synthetic division here, okay? And then what we did was we took this polynomial of degree 3, and we factored this into another binomial and a polynomial of degree 2. That binomial we said was x plus 7. So we have h of x is written as x minus 2 times x plus 7 times 5x squared minus x minus 1. And again, if you're still having trouble seeing what's going on here, what you can do is you can kind of think of x plus 7 times 5x squared minus x minus 1. You can think of that as x plus 2 times 5x squared minus x minus 1. This is actually just equal to this polynomial up here. Okay, so this is equal to 5x to the third plus 34x squared minus 8x minus 7. So really we just took this polynomial and broke it apart. Okay, and then what we did was we took this polynomial and broke it apart even further. Okay, so then we wrote it as x minus 2 times x plus 7 times all of this right here. Okay, so really you kind of take these one step at a time. I know these are really complicated. If you want to see some more examples of these, please feel free to shoot an email my way about maybe a specific one you're stuck on, and I'll be more than happy to do some more examples of these. They definitely take some time, and they take a lot of patience to get through. But this is a really powerful tool, and I would encourage you to make sure you know how to at least do all of the steps involved here. So again, if you have any questions at all, please email me, and have a good